Hey everyone, I want you to do something for me right now. Pull out your phone, look at it. Every text you send, every video you stream, every photo you upload, it all works because of a brilliant mathematician named Claude Shannon. And here's the wild part. He figured out the foundation for all of this in 1948.
Wait, 1948? Before computers were even a thing?
Exactly. Shannon published a mathematical theory of communication when there were barely 10 computers in the entire world. But his paper became what Scientific American called the Magna Carta of the Information Age. Today, we're diving into Shannon's information theory, what it is, why it revolutionized everything, and how it powers your digital life right now.
Okay, I'm intrigued, but information theory sounds abstract. What even is information, mathematically speaking?
That's the genius of Shannon's work. He made information precise and measurable. Let me show you with a simple example. Imagine I flip a fair coin and tell you the result. How much information did I just give you?
I learned whether it was heads or tails.
Right, but Shannon quantified this. Exactly 1 bit of information. But here's where it gets interesting. What if I flip a trick coin, one with heads on both sides, and tell you the result?
That's zero information. I already knew it would be heads.
Exactly. Shannon's insight was revolutionary. Information equals surprise, equals uncertainty, reduction. The more predictable something is, the less information it contains. He captured this with his famous entropy formula, Hx, chamsa SPx, log 2 px. This measures the average uncertainty in bits.
So information is really about what you don't know?
Precisely. And this single insight unlocked everything. Let's talk about where this came from. It's 1948. Shannon is working at Bell Labs, and telecommunications engineers face a massive problem. Telephone lines are noisy, radio signals fade, and everyone thinks the only way to communicate reliably is to either crank up the power or slow way down.
Makes sense though, right? Like shouting louder in a noisy room?
That's what everyone thought. But Shannon proved something completely counterintuitive. He showed that every communication channel has a fundamental speed limit. He called it channel capacity, and you can communicate reliably up to that limit without just repeating everything or using more power. The formula is elegant. C chart B log 2 1 plus Sn, where B is bandwidth and Sn is your signal-to-noise ratio.
Wait, so there's a mathematical limit to how fast we can communicate?
Yes. And here's the kicker. Shannon proved that with sophisticated error-correcting codes, you can approach this limit arbitrarily closely. It's like he discovered a law of nature, the speed of light for information transmission. And just like you can't exceed the speed of light, you can't exceed Shannon's channel capacity. But you can get remarkably close with the right coding schemes.
That's actually beautiful. What was the reaction when he published this?
It shocked the engineering world. Robert Gallagher from MIT said Shannon's work was a blueprint for the digital age, and noted that nobody had come close to this idea before. Shannon's paper created an entire scientific field from scratch. In fact, historian James Gleick argued that Shannon's 1948 paper was even more fundamental than the transistor, which was also invented in 1948.
Okay, so we've got entropy and channel capacity. What else is in this theory?
2 fundamental theorems that changed everything. First, the source coding theorem, which says you can compress any data source down to its entropy, but no further without losing information. Think of it as the ultimate compression limit.
So when I zip a file,
you're approaching Shannon's entropy limit. That's why you can't keep compressing something forever. Random data has maximum entropy and can't be compressed at all. Structured data, like English text, which has patterns, has lower entropy and can be compressed significantly.
What about the second theorem?
The noisy channel coding theorem, Shannon's masterpiece. It states that if your information rate R is less than the channel capacity C, You can achieve error-free communication through a noisy channel with proper error-correcting codes. If R exceeds C, reliable communication is impossible.
But how do you actually do that? How do you encode information to approach these limits?
Great question. Let me show you with Huffman coding, a beautiful example of Shannon's principles in action. Imagine you're sending the message BCAADDD. Normally you'd use 8 bits per character, but Huffman coding assigns shorter codes to more frequent letters. A appears 6 times, so give it code 0, just 1 bit. D appears 4 times, code 10. Less frequent letters get longer codes. The result? You compress about 60% without losing anything.
That's basically what zip files do?
Exactly. And it directly implements Shannon's insight. Frequent events carry less information per occurrence, so they should use shorter codes. The algorithm approaches the entropy limit Shannon defined.
This is fascinating history, but why does this matter today in 2025?
Because Shannon's theory isn't just relevant. It actively constrains and guides every digital technology you use. Let's start with the obvious. Your phone.
Okay, how does information theory power 5G?
5G networks now use codes that are proven to achieve Shannon's speed limit from 1948. For 77 years, we've been developing better and better error-correcting codes, from simple Hamming codes to modern LDPC and polar codes, steadily approaching Shannon's limit. Today's 5G can hit 20 GBPs, and it's working right at the theoretical boundary Shannon calculated decades ago.
So we've basically maxed out what's possible.
For traditional channels, yes. Engineers now work around the limit using techniques like MIMO, multiple antennas creating effectively multiple channels, and beamforming to improve signal-to-noise ratio. But Shannon's formula still governs each channel.
What about compression? You mentioned zip files.
Every compression algorithm you use respects Shannon's entropy limit. JPEG images, MP3 music, Netflix streaming, they all exploit Shannon's rate distortion theory, which explains the mathematical trade-off between file size and quality. JPEG achieves massive compression by throwing away information humans can't perceive anyway, effectively lowering the entropy relative to human perception.
Clever. What about security and cryptography?
Shannon actually wrote a second foundational paper in 1949 called Communication Theory of Secrecy Systems. It's considered the beginning of modern cryptography. He proved that the one-time pad is perfectly secure, meaning unbreakable, and he defined the principles of confusion and diffusion that underpin every modern cipher like AES. Today's cryptographers still use Shannon entropy to measure the strength of encryption keys.
I've also heard information theory is important in AI and machine learning.
Absolutely. Neural networks use cross-entropy as their loss function. That's Shannon entropy at work. Information bottleneck theory explains how deep learning networks actually learn by compressing input information while preserving what's relevant for the output. Decision trees use information gain, based directly on Shannon entropy, to choose optimal splits. And when you hear about KL divergence in machine learning, that's Kullback-Leibler divergence, derived from information theory, measuring the difference between probability distributions.
Wow, so it really is everywhere. Are there any newer, unexpected applications?
DNA sequencing. Researchers use Shannon's entropy to quantify information content in genetic sequences. High-entropy DNA sequences have roughly equal distributions of the 4 bases, while low-entropy sequences have patterns. This helps prioritize which sequences to analyze in massive metagenomic datasets. And here's something cutting-edge. Quantum computing researchers are extending Shannon's framework to quantum channels, developing quantum error correction, and exploring the limits of quantum information processing.
This brings up something I'm curious about. You said Shannon's channel capacity is like a law of nature, a hard limit. Has anyone ever found a way around it?
No, and they never will. Shannon's limits are mathematical truths, like the Pythagorean theorem. You can't compress data below its entropy without loss. You can't transmit faster than channel capacity reliably. These aren't engineering challenges. They're fundamental boundaries of what's possible.
That must be frustrating for engineers.
Actually, it's liberating. Knowing the theoretical limit tells you exactly how much room for improvement exists. In the 1980s, modems were stuck at 9.6 kilobits per second because engineers couldn't find good enough error-correcting codes. But knowing Shannon's limit existed drove decades of research. When turbo codes were discovered in 1993, we suddenly got within a fraction of a decibel of Shannon's limit. That breakthrough enabled the high-speed internet revolution.
So Shannon gave us both the target and the tools to hit it.
Let me share one of my favorite analogies for understanding this. Think of Shannon's entropy like measuring disorder, but specifically, how many yes or no questions do you need to figure something out? A fair coin flip, 1 question, 1 bit. Rolling a 6-sided die, you'd need about 2.6 questions on average, so 2.6 bits of entropy. The weather in San Diego, which is sunny 75% of the time, low entropy, predictable. The weather in St. Louis, sunny 50% of the time, higher entropy, more uncertainty.
So entropy is really just, how surprised can I be?
Perfect. And that connects to compression beautifully. English text has about 1 to 1.5 bits per character of actual information, even though we use 8 bits per character in standard encoding. Why? Because English has massive redundancy, patterns, common letter combinations, grammar rules. Shannon's theory explains why we can compress it so much without losing anything.
Okay, I'm blown away by the applications, but I want to understand Shannon himself a bit more. What kind of person figures this all out?
Shannon was a genuine polymath, and by all accounts, a delightful eccentric. He had dual bachelor's degrees in electrical engineering and mathematics. His 1937 master's thesis on using Boolean algebra for circuit design is called possibly the most important master's thesis of the century. At Bell Labs, colleagues would see him riding a unicycle through the halls, sometimes while juggling. He invented a juggling robot, a flame-throwing trumpet, a rocket-powered frisbee, and even a device to calculate in Roman numerals.
That's amazing! What drove him?
Pure curiosity. Shannon once said, "I am very seldom interested in applications. I am more interested in the elegance of a problem." He co-organized the famous 1956 Dartmouth workshop that founded artificial intelligence as a field. He built chess-playing machines before anyone knew computers could play games. And get this, he created a mechanical mouse named Theseus that could learn to navigate a maze, one of the first examples of machine learning, in 1950.
So he wasn't just the father of information theory.
He's considered a founder of digital computing, digital circuits, cryptography, and a key contributor to AI. Roboticist Rodney Brooks called him the 20th century engineer who contributed the most to 21st century technologies. Yet he remained remarkably humble. When collecting awards, Shannon would often credit his colleagues and downplay his own contributions.
One last question. Where is information theory heading? Is it a solved field or are there frontiers left?
Great question. The fundamentals are solid. Shannon's theorems are mathematical truths that won't change, but applications continue to explode. Right now, major research areas include quantum information theory, understanding deep learning through information theory, biological information processing, and something called semantic information theory that tries to incorporate meaning, not just transmission.
What's that last one about?
Shannon explicitly said his theory was about reliable transmission regardless of meaning. But modern researchers at places like Purdue's Science of Information Center are asking, what if information's value depends on context, time, and the receiver? For example, traffic information is valuable right now but worthless in an hour. That's beyond Shannon's original framework, but inspired by it. Let me leave you with this perspective. Every email you send, every video you stream, every photo you share, every phone call you make, all of it flows through communication channels governed by Shannon's mathematics. The internet exists because Shannon figured out how to send information reliably through noisy wires. Your smartphone compresses photos using Shannon's entropy principles. Netflix streams high-quality video because of rate distortion theory.
It really is the foundation of everything digital.
More than that, Shannon revealed something fundamental about the universe. Information isn't just a human concept. It's as real and measurable as energy or mass. The bit is as fundamental a unit as the meter or the second. And just as Einstein showed us the universe has a cosmic speed limit, Shannon showed us information has fundamental limits too.
That's profound.
MIT professor Robert Gallagher, who worked with Shannon, said, "He had this amazing clarity of vision. Einstein had it too. This ability to take on a complicated problem and find the right way to look at it so that things become very simple." And biographer Jimmy Soni wrote that Shannon's intellect was on par with Albert Einstein and Isaac Newton. Yet John Horgan observed, "No scientist has an impact-to-fame ratio greater than Claude Shannon. He transformed our world more completely than almost any scientist of the 20th century, yet remains relatively unknown outside engineering and computer science." So next time you're streaming music, sending a text or scrolling through social media, remember, you're experiencing Claude Shannon's genius. In 1948, working with slide rules and primitive computers, he mapped out the mathematical laws that would govern our entire information age. He proved what was possible and what was impossible, and 77 years later, we're still working within the beautiful boundaries he discovered.
Shannon figured out the rules of the game before anyone else even knew we were playing.
Perfectly said. If you want to dive deeper into information theory, I'd recommend starting with Shannon's original 1948 paper, It's Surprisingly Readable, or the book A Mind at Play about his life. The math is elegant, the applications are everywhere, and the story of how one brilliant, curious, unicycle-riding juggler changed the world is absolutely worth knowing.
Thanks, Dr. Young. I'll never look at my phone the same way again.
That's the goal. Shannon gave us the information age. The least we can do is understand how and why. Thanks for watching, everyone.